In the 13th lecture, we will study the aircraft response. And in the first mini lecture, we're looking at the aircraft response to a vertical gust. So in order to study this gust response problem, and in this case, from the control point of view, we're simulating the gust as a sharp-edged velocity change. So in this case, the aircraft is subject to a sharp-edged gust of magnitude of Wg, and we see an aircraft is here, and there's a gust with magnitude of Wg, and now the gust is moving upward, and we would say it's an ideal case from the control engineering point of view, but in reality it's not like this, and we will see a more realistic model later. Okay, so the aircraft is flying at a speed of v, and because of there's a gust and relatively the aircraft is moving, has a disturbance velocity Wg downward, and in this case, and there is an induced angle of attack alpha. Okay, since there is a small angle of attack produced, so there will be a lift change and the increased angle of attack can be calculated as Wg over v. And why is this? Because originally it's tangent alpha, right? And because alpha is a small angle, so it's can be approximated by Wg over v. So it's on the small angle of disturbance assumption. Okay, so then there's a changing lift. So delta L can be calculated this way, and we can see delta alpha and also A times half rho v squared times S. So that's the lift coefficient. Then we know A is the slope of CL angle of attack curve, is the slope of that CL curve, and then we just plug in delta alpha by Wg over v, then we can simplify delta L, the induced lift, okay? And we know from the Newton's second law, the second law, the change in force can be calculated as m times vertical acceleration. Is that right? Okay, and then the maximum vertical acceleration. Why maximum vertical acceleration? Because now we are having a sharp edge gust, so this will produce a maximum acceleration. So the maximum vertical acceleration can be calculated by delta L divided by m, and then we can have this vertical acceleration. And since we've discussed the load factor n before, so we would like to represent this problem by the load factor, because the load factor measures whether that section of flight is comfortable. Yeah, we don't expect larger load factor for the passenger, especially for passenger aircraft. And we know for load factor, when the aircraft is in level flight, and the load factor is 1. But in this case, on a gust, vertical gust, what happens? So on a vertical gust, the load factor is what we calculated, the vertical acceleration plus 1. So we have this expression for the load factor on the vertical gust. So this is a derivation so far, and you can see in the last line we have Wg hat, and that's a non-dimensional vertical gust magnitude. Okay, so I'm writing it again, the load factor for the aircraft on the vertical gust. So we would say this is the maximum instantaneous value, because the aircraft will quickly acquire the vertical component of velocity Wg, because it's a sharp-edged disturbance under the assumption at the beginning, because it's easier to process. And a more complete analysis will solve the differential equation for the vertical velocity w in terms of time to obtain the following expression. So if we want to study it completely, in a complete manner, in a complete fashion, and we need to solve a differential equation, and then we're showing the solution for that differential equation as here. So we have the dimensional form and a dimensionless form, and I'm not going to solve this differential equation here, but we can see generally the result format of the result. So we have the dimensional form and a non-dimensional form, and you can see in the bracket we have the e exponent, right? So it is not a linear change as we assumed before. Okay, so if we plot the change in vertical velocity versus time, we would have this kind of plot. And I just want to highlight, you have a negative sign here. Okay, so you can see the vertical velocity, actually the inverse of the vertical velocity will approach wg eventually. So this curve will approach infinitely to 1. That's wg. Okay, so do you realize why we need to include such a negative sign? Because the positive wg is pointing downward, right? So that's why we usually plot a negative sign before this w. Okay, otherwise it become negative 1. Okay, so you can see from here, and from the realistic, more complete analysis, the w will approach wg after a certain amount of time. So, and now let's do some detailed measurement. If we calculate the time roughly when the vertical velocity approaches 90% of wg, so that takes about half of the characteristic time. And just to let you know, the characteristic time for lighter aircraft is usually 1 second. For larger aircraft is about 5 seconds. You can see it's the response to the vertical gust is very quick. So for light aircraft is about let's say half a second to obtain the 90% of the vertical gust magnitude. But for larger aircraft, it takes slightly longer, but still quite a small value, 2.5 seconds to have the 90% of the WG, vertical gust magnitude. Okay, so this is what we've discussed from the step change gust, and the peak value of excess G loading. So we are talking about the excess G loading, just -1. So that's the maximum excess G loading we can achieve by using the step change velocity model. So we need a smaller, in this case, and in order to have a smaller G loading, excess G loading, what can we do? And we actually need a smaller a. What is a? A is the slope of the lift coefficient curve, and a larger CL. So in this case, we can minimize the excess G loading. That's what we usually do in practice. And knowing that the most comfortable ride in an aircraft is during vertical gust is thus obtained in low aspect ratio. If the aspect ratio is lower, which means we can have a smaller a, and also higher altitude and with higher wing loading. Why higher wing loading? Because in that case CL becomes larger, so we have smaller n. Okay, so this is what we conclude from the previous slides. And if we see a actual plot, and so this excess G loading changes versus time is plotted in here. So the excess load factor for a gust of 25 feet per second, which is about 7.6 meter per second, and the aircraft's true airspeed is 200 knot, and CL is 0.4. The lift curve slope A is about 5. Then the sudden increase of excess load factor is larger than 0.9. So you can see at the beginning, the initial value excess G loading is about 0.9. This is very uncomfortable because it's if we +1, the G loading is already 1.9. And if you are sitting in an aircraft, if you're a passenger there, you will feel really uncomfortable. So this is what happens for to examine the G loading or excess G loading during a vertical gust. Under what kind of model can you remember? A simple step change velocity. So the gust is simulated by a step changing velocity magnitude. Okay. So remember, the result is from a step function of gust. All real gusts will be less viscous. And so this is the most extreme case. That's why we usually put a maximum in analysis. Okay, so now let's see a more realistic model by taking into account the realistic effect, which means we will not use the step change model, but the other model. Which model are we going to use? Let's see. So the step function on the previous slides does not happen in practice, because there won't be any such a step change. Usually it's a gradual change in velocity magnitude, right? A more realistic analysis could be performed through a profile of 1 minus cosine type. So we are using the 1 minus cosine to simulate the velocity, gust velocity change. Why this? Because this kind of profile is closer to the velocity profile of an air jet. So vertical gust is kind of a vertical jet, and then we want to use a velocity profile similar to that, and we can have a look. So this is the expression for vertical gust profile distribution, velocity profile distribution, and we can see it's related with the gust magnitude and also h. And let's see what are the meaning of h. And before that, let's first see the velocity profile distribution. So this is a gust velocity under the 1 minus cosine profile, and we can see the x-axis, horizontal axis, is x over c. C is the chord, mean aerodynamic chord of the aircraft, and the vertical axis is w over wg. So that's the simulated vertical velocity. Okay, and then we can see x is actually the distance traveled in the direction of light, and we know c is the mean aerodynamic chord. In this plot, x is within the arrow and 2h, and you can see h here is half the distance over which gust acts. So the gust spans about 2h, and in this specific problem, it covers an area of 25 or length of 25 c, and the location at h, x over a, x equals h, is where the peak gust velocity happens. So you can see this is actually similar as a jet profile. That's what we want in the more realistic model. Okay, and in this case, 2h is 25 c. So you can see the inference area for the vertical gust is about 25 times of the chord. Okay, and we've already known or derived this maximum excessive G loading from the step function. And if we use the current realistic function, and we can express, usually we express this maximum G loading under the realistic function, which is 1 minus cosine profile, and we can just very similar as the one above using the step function. So we have an additional kg on the right hand side. What is kg, you may wonder? So the kg, we call it the Gust alleviation factor, and it's expressed, can be calculated this way: 0.88 mu divided by 5.3 plus mu. And mu is usually a function of aircraft mass, gross wing area. So it's a combination of the aircraft properties and also the local air density. Okay. And usually for light aircraft, mu is about 15, but for larger passenger aircraft, mu is between 30 and 40. And so we know the range of the mu, and if mu was very large, and then the kg will approach 0.88. So it's, even if it's 0.88, it's still very about 88% of the maximum excessive G loading on the step function. Okay, so in reality or in practice, most aircraft has kg between 0.65 to 0.8, which means it's 60% or 80% of the G loading, excess G loading of the on the step function. Okay, so if we see a plot by plotting n-1 versus the non-dimensional characteristic time, so we can see it will reduces progressively, and this is from the, actually we've seen this plot, and it reduces progressively, so the excessive G loading will approach 0. And remember, this is under the step function, original Gust of step function. So let's say if we have the realistic function, which is taking into account the jet profile of the vertical gust, so the evolution will look like this. So the initial downward part will be replaced by the upward part and then downward. So the red part is a modified curve, provides a more comfortable peak acceleration. And the peak is about 40% or 42% of the step function magnitude. So it's reduced to half of the initial maximum acceleration.